There's never been a time when a resource has held as much power to shape our world as data does today. I'm Paul, and on this podcast, we explore how innovators are using data to transform how we live, work, and create. Today, I'm joined by Stephanie Hernandez, Senior Engineering Director at Seagate, to discuss Mozaic, a breakthrough technology that arrives at a critical moment in time when AI is generating unprecedented levels of storage demand. Let's get into it. Welcome to the Data Movement. Stephanie, welcome to the show, first of all.
Thank you for having me.
Yeah, of course. Amazing to have you here. I'm super excited for a variety of different reasons to have this conversation. I want to start by going back in time. You've been with Seagate for 15 years, and I want to kind of explore a little bit around your journey with Seagate, your perspective on the storage industry and the shifts that have happened in that time. And it feels like we're in the midst of one at the moment. So maybe let's start there. What have you been doing at Seagate for the last decade and a half?
I started at Seagate as a reader designer. So, going back a little bit further, I did my Ph.D. at the U of M, and I actually was working on magnetic recording even as a graduate student. So I worked in the lab of a professor called Randy Victoria, and his focus was on designing and looking at advanced HDD technologies. And his work was more computational, which was really fit in with what I am interested in. What I am interested in, what I was interested in at that time. And that, he was funded by Seagate, and that, of course, led to internship opportunities at Seagate and eventually landing a role as a reader designer here in Minnesota about 15 years ago. And I was a modeler, so meaning I used physics-based models to understand how our reader designs should scale as a function of, areal density and to get the performance that we need. Eventually, I moved on to the research group, which fit a lot better with what I'm interested in. I like figuring out what will be the technologies 10 to 20 years into the future. So I joined the Seagate research group, also here in Minnesota. And then I really started modeling heat-assisted magnetic recording. So at that time, when I joined, it was a future technology. Now it's a reality. So now I lead a group that's looking at future HAMR technologies and even looking at what are post-HAMR HDD and alternative data storage technologies.
Yeah, amazing. So let's start with talking a little bit about HAMR. Super topical at the moment in the industry. Seagate, at least by the time this episode publishes, we will have made a big announcement around new areal density capabilities that are unlocking capacities into the 40 terabytes per drive, and some of the things that our customers are doing with those drives today. So I want to go back, before we get into that, I want to go back to Stephanie, 13, 15 years ago when you started. What was the perception of HAMR at that point?
Yeah. Throughout my Seagate experience, I have experienced that transition from perpendicular magnetic recording to HAMR in the design groups. I can't overstate how significant of a transition that was. Before HAMR became what most of us are working on, people were skeptical. There was still a lot of challenges that needed to be resolved in order to bring that technology to pass. There are significant changes that were required. You needed brand new media design, brand new head design. You needed a head that has now optical elements. You still needed reader technology that keeps up with the areal density and capacity increases. And all of the parts of the recording system have to be designed to be able to support that increased capacity. So there were still a lot of issues and other challenges that needed to be resolved to get to where we are today. So certainly there were a lot of skeptics at the time, but as we learn more, right, as the design evolves, it becomes clear that yes, this is fundamentally a technology that's very viable. And the challenges are engineering challenges that through continuing to understand, HAMR, we can overcome them.
Yeah. And I imagine, was the skepticism around whether the technology could fundamentally work, or was it more about, at that point at least, we'd proven that it can work, it's just can it scale to the level that the previous gen PMR technology could? Or maybe a bit of both.
Right. I think people have always thought that it's a technology that could fundamentally work in terms of, yes, you can record smaller bit sizes with HAMR, but how do we design a system that can operate in real life out there in the real world with the reliability and performance requirements that are necessary to deploy, such products. We always thought it was scalable. I mean, it always became more clear as time went on, but certainly, making sure the device is robust, that was one of the biggest challenges.
Yeah, it's so interesting to me because I've got, like, on my desk here, right? I've got a prop, and this is a Seagate drive. Maybe actually it's probably close to 15 years old. So when you kind of first started looking at this stuff when you joined, is a 4 terabyte. It's a 4 terabyte, 3.5-inch drive. And one of the most interesting things for me is about hard drive tech is the form factor is, like, even though it's a 15-year-old product, the form factor, the dimensions of the thing, this little gray box, is the same.
Mm-hmm. Yep.
Right. And there are specific reasons for why that is. Like, you can't change the form factor. So all of the innovation that you just kind of alluded to at a really high level is actually going on inside this little rectangular box, which is just it's such an interesting engineering and creative challenge. Can you talk through, like, the other thing in relation to that question is this idea of, like, superparamagnetic recording, or the limit. Sorry. Yeah. Superparamagnetic limit. Can you talk about what that is and why it's important? Because I want to dig into the technologies inside that help solve for that.
Right. So for many, many years, people have been predicting the death of a hard drive, right? What is the limit to how small of a bit you can record on magnetic disks in a hard drive? And so the superparamagnetic limit is just saying, if you reduce the particle size of a magnetic material, it becomes very thermally unstable. So instead of magnetic, it becomes paramagnetic. So it's not magnetic anymore. It doesn't hold any information. And, we've had many different technological evolutions over these, 20, 30 years, and before then, of course. And each of these critical technological changes have provided an opportunity to keep beating the superparamagnetic limit. So we've been able to incorporate new designs new media designs specifically that are able to support smaller and smaller grain sizes. So the disks in the hard drive, the recording material is it's a granular magnetic material. And you have these grains, which right now they're about 10 nanometers, less than 10 nanometers. And each technological evolution has allowed us to bring a new media design that is able to support smaller and smaller grain size. So we've been able to beat the superparamagnetic limit, and we don't know exactly when the actual limit will hit us. I mean, eventually, yes. But we think that the technology that we're at right now, heat assisted magnetic recording, can take us pretty far.
Yeah. So, and tell me about the grain size and why that's important in this kind of equation.
Yeah. So the information, it's written on the disk in these tracks. So tracks are the sequence of bits, and the sequence of bits determines, it makes up the data, right? That's written on the disk. And each bit is a fundamental unit of information. It's a 1 or a 0, or a 1 or a -1. And these bits are collections of grains that are magnetized in the same direction. And so in order to keep reducing the bit size and maintain the signal to noise ratio, so the signal to noise ratio is a really fundamental metric that's important to us because we want to sense a strong signal from the media with reduced noise as much as possible. So in order to reduce the noise, we need more grains within a bit. So I can't just reduce the bit size without reducing the grain size as well. So that's why it's been so critical to shift to different recording technologies that are able to support smaller grain size.
You kind of alluded to a few of the innovations that make up HAMR, or Mozaic as we refer to it as at Seagate. What are some of those kind of fundamental components or subsystems that make that up?
Yeah, so I talked a lot about the media, so maybe I'll start there.
Yeah.
So for HAMR, the media is fundamentally different than PMR, completely new media design. The material is iron platinum based, and it has very high magnetic anisotropy. That means that it's always challenging to fabricate media with small grain size and very good properties. But by virtue of having that high anisotropy, you could push the grain size much further than you can conventional media designs. The reason we can use iron platinum is because now we have a brand new writer. In perpendicular magnetic recording, we have magnetic writers that supply a field if this is the media plane, then the field is perpendicular to the media plane. And the bits are magnetized also perpendicularly to that media plane. With HAMR, that's all still true, but now we need an additional excitation in order to write this very high anisotropy media, because iron platinum is very, very thermally stable, very, very magnetically hard. But that means it's very, very hard to write. I can't just take a PMR writer and record information on it because of that robustness. So that means I need to supply some kind of assist in order to be able to record information on this new high anisotropy media. Mm-hmm. And the best way, really the only way we could really do it is by applying heat. But you want to apply heat not all the time, but only during the write process. So magnetic materials have this property where they lose their magnetization, they lose their anisotropy and magnetic hardness as a function of temperature. So we want to apply just enough temperature, but only when we want to write the bits. And that's why a brand new writer needed to be designed that has, again, a magnetic writer, because we still need that to supply the excitation needed to write the bits on the disk. But we also need now an optical writer, which It's brand new to HAMR. You need a laser that supplies that heat input. You need an optical waveguide that will take that energy from the laser all the way to the air-bearing surface, which is that area right next to the media. And then it's an innovation called a near-field transducer that can efficiently direct that energy to apply a very narrow, concentrated heat pulse on the media. So very different media, very different writer, right? Those are the let's say the fundamental changes. However, the entire system has to scale. You need readers that are able to sense those narrow tracks. You need the interfaces to be, you need the head-disk interface to support these new components. So the distance between the head and the media has to be reduced. You need these coatings and layers on the heads and the media to be thin. To support that small spacing, but also to have thermal robustness and be able to protect the media under these extreme recording conditions. And also the mechanics also have to support that very high track pitch. So for HAMR, yes, there's the heat-assisted magnetic recording part, but the entire system has to support this brand new recording mechanism.
It sounds like something out of science fiction, you know? when you're talking about lasers heating up parts of that spinning disk, and can you talk to the level of precision, right? Because this is just so compelling when I learned about this.
If you take the distance between the head and the disk, you can't even fit a DNA strand in between the two. You could fit the entire writer structure within a red blood cell. And these are analogies from probably 10 years ago. Now it's all atomic level precision. We have, all the components right now are on the order of tens of nanometers. So hundreds of micrometer sized components. And yes, the manufacturing process has to support that aggressive scaling. The mechanical system has to be able to accurately track and place the head exactly where it's supposed to be on the disk, and tracks are only tens of nanometers in width. So all of these systems continually work together to be able to achieve all of these high capacities from 30 terabyte to 40 and beyond. Yeah,
I've heard you and your colleagues, when you're talking about this technology, is like atomic scale engineering is literally that bit that you're applying the heat to with the laser is less than an atom's diameter or something to that. Like the pinpoint heat application is happening at that size, and it needs to heat it and cool it down. I think 800 Fahrenheit is the temperature that you've got to heat that spot to on the disk, and then it cools down again in a nanosecond or something. So it's like if the engineering is happening in terms of speed and size at completely different scale. Right.
Yeah, the heat spot is 800 degrees Fahrenheit, only a few grains wide, a handful of grains wide. And that's even now for Mozaic 3 and 4. But once we talk about 10 terabyte per disk, those geometries get even more aggressive.
Yeah, and it's like all of this stuff, as well, all of these kind of these nanoscale or these tiny systems and components. It's not like you can go to a store or go somewhere and just buy them, right? They're all bespoke, right? So, am I right in saying that? Like we've custom built pretty much all of them, right, for this specific use case. Can you speak a little bit to that?
Yeah, I mean, Seagate has committed to HAMR from the beginning, right? We're the company that said HAMR is the path forward. So we had to design everything from scratch, right? Figuring out the physics of the HAMR recording system, figuring out, how to incorporate optical technology in a write head, all of the media development in-house to support, the development of this new media. Everything is designed in-house. So we have just a collection of amazing knowledge, right? That we had people that had to become optical write head designers. And even now we're exploring completely new designs that, we're just starting to develop and think about. So while we may take information from what's going on externally, right? We attend conferences, we fund universities, and we try to figure out what are the trends and what's the learning going on in the outside world. We take all of those pieces and try to come up with, how do these new technologies, how can we take them and make new heads, new readers, new media? And that's all done in-house.
Mm-hmm. What about I mentioned this sounds like a, jokingly, this sounds like a science fiction movie. It doesn't seem real, but it very much is, right? And it's not an R&D project, right? Now we're producing millions of these things, right? Packaging them up as these kind of, these little gray boxes and sending them out into the world. And so what's so interesting to me about about the hard drive industry, or what Seagate does, is we're dealing with atoms, we're dealing with nanometer scale engineering, but then it's so tiny, right? To be able to fit these, more and more bits in this tiny little 3.5-inch box. But then we're mass producing them by the millions, so I think, multi-exabytes of storage capacity every day, coming off our manufacturing line. So the interesting dichotomy is, we're truly engineering at a tiny scale, but mass producing at an enormous scale. And now HAMR, we're doing that today. Can you maybe speak to that process, like how we were able to, produce that amount of exabyte output per day? What goes into doing something like that? It's one thing to be able to produce one of these things, right? It's another thing to be able to produce millions of them at the scale that we do, and store the world's data, right? Which is which is what we're doing. So it's like everything from finding the materials, right, building the components. There must be millions of that we're producing all in the house, millions of these components, integrating them, testing them, like you said earlier, for performance and durability. All of the machinery, the manufacturing,
right,
the people, the processes, all of the orchestration, and in doing that is just a it's a pretty mind-blowing operation to think about it like that.
With any of these technologies, it started as an idea, right? For any of these new technologies integrated from generation to generation, it started as a research project, right? Which may be one or two people. And then we add more people, the more promising the project becomes. We start maybe using some of our existing tools to explore some of the concepts, or maybe partnering with some external partners to look at, whether or not the technology is feasible, and step by step, it moves down this funnel, right? Where we have a lot of technologies on one end, and we evaluate all of them at a low level. And then the next step becomes we involve more people in the process. We do more internal work. If the technology becomes viable, of the few that made it that far, then only one or two go forward to the next stage. And then we start incorporating more of our existing processes, right, into developing these new platforms. So step by step, it moves from research to development. And within development, it just moves closer and closer to productization. So it's a gradual transition because you have to first understand, the intricacies and the recording physics and all of these different things before you move on further down, the maturity cycle. But then, we have a manufacturing process that's well established, and you have to modify that manufacturing process step by step to accommodate these new technologies. So it's certainly not a switch that you pull, right? And you go from PMR to HAMR, right? It's a very gradual process where it starts with a dream, an idea, and then little by little, more of our people are involved until now it becomes this, thousands of people effort. And then eventually we can produce something to give to our customers.
So you mentioned our customers. Like, why does any of this matter? Like Seagate doing crazy stuff with quantum physics and innovating with these little boxes. Why does it matter to our customers? Why does it matter to the world?
I think ultimately our customers are interested in higher capacity, right? In a box that you can just plug in and it behaves in much the same way and has good performance, right? I think they're interested in the technologies that are going into this box because they want confidence that we have a plan for advancing the technology. And, we've always projected that the world will create data at an exponential rate, and there will never be enough drives to store all of them, but we still have to keep increasing capacity because, we do need to store a lot of the data that's created. That's becoming more and more important. So ideas to keep increasing capacity within the same form factor are very important.
The typical kind of like the high capacity stuff, the Mozaic HAMR stuff. What are the kind of key environments that those drives tend to end up in, and why?
Yeah, so all of our mass capacity drives, they end up in the big hyperscalers, right? They're the ones that have limited footprint, right? So we need to keep providing drives that have increased capacity and can support increasing the capacity available without increasing the footprint of the data storage system. So we all know the names of these hyperscalers and our cloud service providers, and we all use their services, right? We all store a lot of data, and we generate a lot of data that we want to be able to access. So it becomes important to supply a device that can support that, the growth in data over time.
It goes back to the idea of not messing with the form factor, because it's got to slot into those. You can't rip and replace or change up the format of these data center slots. You've got to stay, you've got to innovate within those parameters. And yeah, like you said, the crazy growth in data, also the value of data, the retention periods for that for the data, accessibility for data, all of these kind of dynamics are driving up storage demand. And I guess like why it matters is just trying to help our customers keep pace with that growth curve. An interesting kind of customer scenario that I was looking at yesterday is just the idea of, when you're at this kind of fleet scale, right, where you're operating a fleet of drives into the hundreds of thousands and beyond, the impact, like when you're at exabyte scale of like an upgrade scenario from maybe a fleet of 20 terabytes drives to a fleet of 40 terabytes is you're essentially doubling your storage, your raw storage capacity within the same physical footprint, right? And you alluded to earlier, one of the challenges today is just kind of space, physics, right? There are limitations to physics, just like there are limitations inside the drive. There are limitations on the environments that these things slot into. And so why is areal density important? I think that speaks to that, right?
Yeah, I mean, everything that we're working on is, just pure areal density. I mean, not all of it, but a lot of what we're working on is how do we keep increasing areal density by just decreasing or increasing capacity by decreasing the size of the bit. So all of these technologies can really fit within the box size that we have. So that I think is the way forward to being able to keep increasing capacity to 100 terabytes, right? Because it's pure areal density.
You mentioned something earlier that caught my attention, 10 terabytes per disk, right? So Mozaic, we're at 4 plus, right? And you're looking future state, like how do we keep innovating with areal density to increase capacity over time? Like what are some of the ways that you guys are thinking about that you can share with me?
Absolutely. Yeah. So, we don't see any fundamental roadblocks from between 4 beyond, right, to 10 and beyond that. It's a matter of, like I said, it's all about increasing pure areal density. So that requires decreasing the size of the components. So the reader has to be smaller. The critical write elements also have to be smaller because and the grain size has to be smaller to support smaller and smaller bits. So we've actually demonstrated in the lab 7 terabyte per disk. So that's, double-ish from where we are in product today.
Cool.
And this is in a real lab. So we're actually taking next generation heads and media and recording real information on the disk and recovering that information. Now, the components, they're much more aggressive than what we have today in terms of geometry. So that system, that 7 terabyte per disk system, is not immediately productizable. But it serves as a proof of concept for what is achievable in a recording system. Another thing that's in the demo is multi-sensor magnetic recording. So we do signal processing to mimic having 2 readers. And that allows us to use narrower readers, but we need 2 of them in order to resolve the information coming from narrower tracks. So we've proven 7 terabyte per disk.
You have 1 reader today. So
we have 1 reader today in HAMR. Yes. Yeah. So if we put 2 of them, we could use narrower readers than we would otherwise be able to. Because like I said, magnetic materials become unstable at small volumes. So yes, with HAMR, we can write really narrow tracks, but the reader also has to be narrow. So if we want to get to higher and higher areal densities, our readers also have to be narrow. So using 2 or more readers, we can actually reduce the size of the reader than we would otherwise be able to. So in these areal density demos, there's also mimicking multi-sensor magnetic recording. So again, we can use narrower readers than we would be able to put in a product today. But these demos, demonstrate we could write bits that are small enough to support 7 terabyte per disk. Now it's a matter of actually producing these narrow features, narrow components in a reliable way. Now, beyond 7 terabyte per disk, there are many more ideas. So taking different multi-sensor magnetic recording technologies, we can do two-dimensional magnetic recording. So that's a different way of encoding the information on the disk. I still need 2 readers. And there's this other concept called vector recording, where I'm sensing different field directions that are coming from the written patterns on the disk. And ideas like these are able to relax the reader width scaling issue. So I can use wider readers than I would otherwise be able to. So we also need new mechanical systems to support this very high track pitch and be able to support these multi-sensor magnetic recording technologies that require very precise distances between the 2 readers. And so we're looking at new reader materials, new reader designs. We're continuing to scale the critical dimensions of the HAMR writer, continuing to reduce the media grain size, use new media materials to support smaller grain size. So yeah, lots of ideas to get to 10 terabyte per disk. Still a lot that needs to be worked on. We're partner, like I mentioned, we partner with a lot of different universities to explore different concepts. There's new ideas that we may not have the expertise to explore in-house, that we partner with different researchers, and they can look at these technologies, and we might eventually incorporate them into our designs. So there's still lots that needs to be figured out to get to 10 terabyte per disk and beyond. But we think HAMR is highly scalable. Like the HAMR is a very good framework to build new technologies off of. It just fundamentally supports capacity and areal density growth. And then it's just a matter of seeing how far that will take us, which is still an open question, but we're confident that we can certainly get to 10, and beyond that, we'll have to see how far HAMR can take us.
Yeah, so the HAMR paradigm holds like beyond, like to 10 terabytes per disk, and we think beyond, it's again the principle of just shrinking the components and the systems and innovating around that nanoscale engineering in order to get to those areal density milestones. Yeah.
Always reducing the size of the components is key, right? That's what drives areal density. And, also thinking of new ways of recording the information on the disk. So how can I record more information while relaxing the bit size, while relaxing the different component geometries? Those are also things that we're thinking about. But yeah, I think ultimately HAMR is able to achieve 10 terabyte per disk and beyond that. And it's just amazing that hard drives have been around for many, many years, and you have one there, and from the outside the box looks the same today as it does for that box you have there. But if you open it up, it actually also looks the same, right? So when people first designed a hard drive, did they really think that same design would be able to support 30, 40, 100 terabytes? Because not all you need to do, but it's such a well-designed system that it supports these extreme geometrical scaling. The mechanical systems, all of that can support these extreme geometries. So our goal is to maintain that rotating disk architecture for as long as possible.
Yeah. Do you have like beyond that age old rotating disk architecture that has survived multiple technology transitions and is still storing the world's data today? Do you have research projects or ideation outside of that kind of core innovation path? Are there other interesting recording technologies that are interesting to the company?
Yeah, I mean, our fundamental goal is to keep extending that rotating disk architecture and even beyond magnetic recording. So eventually we'll hit that superparamagnetic limit and we won't be able to keep reducing the grain size. When that would be, we don't know. But there are other types of materials that could replace magnetic materials. There's ferroelectrics, there may be others that could serve as a recording medium that could store information at smaller bit sizes than magnetic materials are able to. So that's all very much a very speculative research project. And it's in the realm of just doing fundamental physics modeling, partnering with universities. Beyond rotating disk architecture, we like to look at things like DNA data storage, or just looking at trends in other non-HDD type architectures. However, there's really nothing that they're looking at that will be an HDD replacement. HDD sits in a very specific place in the data storage hierarchy. And, none of the technologies that are being talked about are HDD replacements. We're trying to see what can go into the HDD to continue increasing the capacity of the device.
Yeah. It's almost like these are adjacent fields of research that we would look to try and integrate into our core architecture. Is that right? Is that why we study it? Just to see if are there things that we can learn and pull into our core roadmap?
Well, I think Seagate should be involved in more parts of the data sphere than just HDD, right? We need to figure out if there are other opportunities for us to be involved in these other parts of the data sphere.
I think we need to wrap up. Stephanie, it's been such a fascinating conversation. What didn't I ask you that's important for our audience to know about this technology and the work that you do? Why would I choose to work in magnetic recording, right? Because that's not a typical field that, grad students back in the 2010 would go into, right? But as a student and even as I became, an engineer at Seagate and I was learning about all the technologies, it's amazing how many diverse technologies are in a hard drive and how much these technologies have evolved over time. And I don't think that's something that's clear to the world, right? Open the box looks the same on the outside and the inside. But if you take a microscope or something stronger than that and look at, all of the different components are completely different materials, right? Completely different physics used to do all the things that a hard drive does. And, I think people should know that, a hard drive is much more than what it looks. It's amazing technology. It's just amazing how much it scaled over time. It changed over time. Yeah, it's like the allure of, working on a startup that does nanorobotics, for example. It's like that sounds like something an engineer, like an up and coming new, fresh grad out of school would be super interesting, compelled to work on. That's a hard drive, right? it's a robot, it's a nano robot that is delivering incredible value to the world. And yeah, like you said, like it's such a well-designed system that what you can see with the naked eye actually hasn't changed in a few decades. But it's like it's what's on the inside, right? It's under the microscope. Then you're so many incredible innovations and technologies being brought together and integrated and then manufactured at mind-blowing scale. Really, really phenomenal.
Absolutely.
Yeah. Stephanie, it's been such a pleasure chatting. I learned a ton about about the work that you do, and you really helped educate me on some parts of what the company does that I wasn't quite as aware of. So I appreciate you walking me through that, and appreciate your time today.
Thank you so much for the opportunity. It's been a pleasure chatting with you too.
Yeah, can't wait to see like those next innovation nodes and hitting 7 terabytes a disk and 10, and all of the work you and your team and your colleagues are driving here at Seagate. Super impressive.
Thank you so much, Paul.